Good morning, everyone. My name is Kevin. I'm currently a joint JD PhD candidate at Harvard Law School and MIT. I wish I could be with you all in beautiful Bristol, but I do look forward to interacting with you all virtually for now. And today I'll be presenting joint work with my co-authors Henry and Dan on a new cryptographic technique for improving privacy in recent privacy-preserving online advertising systems. So retargeted ads are the ads that follow you around the web. Suppose you visit the website of a shoe retailer, you add a pair of shoes to your shopping cart, and then you browse away without making the purchase. Then, over the next week, as you browse through your favorite news sites and blogs, you see ads for that exact pair of shoes. Now, this is a familiar experience to many, but what goes on behind the scenes is perhaps less well known. Behind the scenes, an ad exchange has been tracking your web browsing activity using third-party cookies and profiling you based on the websites you visited. And later, when an opportunity comes up to show you an ad, the exchange coordinates with a large number of advertisers and other intermediaries to auction off the chance to show you an ad to the highest bidder. So in the time that you wait for a web page to load, a multitude of parties have gained a snapshot into your preferences and your online behavior. To address these privacy issues, major browser vendors, including Google, have recently begun to deprecate third-party cookies. But in response, they've also introduced various proposals to support the different kinds of targeted advertising in a third-party cookieless world. In this work, we focus on Google's Protected Audience API. This proposal for private ad retargeting shifts the retargeting pipeline traditionally done by the ad exchange to the client's web browser. And this not only grants clients privacy, but also transparency into and control over the retargeting process. However, the Protected Audience API doesn't yet consider how to maintain privacy in the billing process. In other words, how the exchange will correctly charge advertisers and pay publishers for ad impressions without requiring the exchange to collect sensitive client data. So in this work, we first identify private billing as a key missing component in the Protected Audience API. Second, we propose that the exchange use an eCache scheme to privately bill for ad impressions without needing to learn clients' web browsing activity. And to that end, we design a new divisible eCache scheme that is well suited for this setting. And finally, we show that our private billing solution is practically efficient, offering low latency, low client costs, and low server operating costs. So to set the stage, I'll go through the main participants in online advertising. First, clients browse the web, visiting advertiser and publisher websites. Advertisers pay to retarget ads to clients who have previously visited their websites. Publishers monetize their websites by showing ads to clients. And the exchange acts as a broker, matching advertisers to publishers. And of course, the central role of the exchange gives it unchecked access to clients' web browsing activity. With the Protected Audience API, things look a bit different. At a high level, when the client visits an advertiser's website, the advertiser sends back what we'll call a callback URL, which the client's browser can later use to set up retargeting opportunities. When the client visits a publisher website that wants to serve a retargeted ad, the client's browser uses the stored callback URLs to run a local auction with advertisers it's visited before to determine a winning advertiser. The client's browser notifies the winning advertiser, and the winner sends its ad to the client. And finally, the browser displays the ad in a fenced frame, which prevents the publisher from seeing the displayed ad and inferring who the winning advertiser is. And the Protected Audience API is indeed good for privacy. Adidas doesn't learn that its user reads the New York Times. The New York Times doesn't learn that its user is in the market for Adidas shoes. And so far, there's no need for a traditionally privacy-invasive exchange. But the problem is that billing becomes more challenging. Owing to the Protected Audience API's privacy guarantees, the exchange doesn't know who to charge and who to pay for ad impressions, Yet private billing is a necessary piece of a functioning private advertising system. To accommodate private billing, we propose to reinstate a limited exchange that uses an eCash scheme to privately bill for ad impressions without needing to learn clients' web browsing activity. In our setting, eCash involves two parties, a customer and a bank. In the issuance phase, the customer sends fiat money to the bank, and the bank issues eCash in return. The customer can spend the eCash by sending it to another customer, and then in the redemption phase, the other customer can redeem the eCash with the bank and receive fiat money in return. Importantly, eCash is unforgeable, meaning that customers can't mint money out of thin air. And it's also unlinkable, meaning that the bank can't link redemptions to issuances. Now, integrating private billing with protected audiences looks like the following. First, advertisers obtain electronic coins from the exchange. And then, as usual, the client visits advertiser websites, stores the returned callback URLs. The client then visits a publisher's website, who returns a web page with ad space. The client runs the local ad auction, and the client notifies the winning advertiser. But now the winning advertiser sends both an ad and coins for the winning bid price to the client. The client forwards the coins to the publisher, who in turn redeems them with the exchange. The exchange checks the validity of the coins and if they've been double spent. And if the exchange accepts, then it returns fiat money to the publisher. The publisher notifies the client that the payment was successful, and the client displays the ad in a fenced frame. And again, Adidas doesn't learn the client reads the New York Times. The New York Times doesn't learn the client is in the market for Adidas shoes. And the exchange doesn't learn the advertiser-publisher links. But yet, everyone is properly billed. We identify Divisible eCash as the right tool for the job. Divisible eCash allows the customer to trade in N dollars and get back a bag of N coins. When the customer wants to spend a certain number of those coins, it can do so in powers of 2 and get back the right number of dollars in exchange. The upside is that divisible eCash schemes are asymptotically efficient. The downsides are that these schemes are quite complicated and they can have expensive concrete costs. So in this work, our goal is really to simplify these schemes and to improve their concrete efficiency. While I won't have time to go over our construction in detail, I will point out the highlights. So we designed the first divisible eCash scheme, to our knowledge, that leverages modern zero-knowledge proofs. It's also the first scheme to go from a linear to a logarithmic number of pairings. And we also use a new collision resistance property of pseudo-random generators. In our benchmarks, we find that our scheme is practically efficient. It adds low overheads to the protected audience API, less than 63 milliseconds of ad delivery latency, negligible client computation, and less than 3 kilobytes of client communication. We also achieve a 250x reduction over the state of the art in the ad exchange's computational cost. And we achieve a combined server operating cost, which includes advertisers, publishers, and the exchange, of less than 1% of ad spend, which is a 5x savings over the state of the art. Now coming to limitations in future work, one might reasonably ask, well, can't malicious clients steal the coins and redeem them for themselves? And indeed, ad fraud is a challenging problem in our system as it is with today's advertising systems. We do describe some mitigations in the paper, but there's nothing absolutely bulletproof. One might also ask, is the latency overhead of our scheme sufficiently low? For a target of delivering ads in under 150 milliseconds, that leaves 87 milliseconds for the remainder of the protected audience API, which we would hope is a sufficient amount of time. And finally, is the operating cost low enough for practical deployment? While achieving an operating cost of less than 1% of ad spend is a good achievement, Given that the advertising industry is approaching a $1 trillion industry, there's much more work to be done to make this practical, and we hope that we've inspired you to join us in this research. So with that, thank you for listening to my talk, and I'm happy to take any of your questions.